For this last mini lecture for motion in one dimension, we're going to talk about graphical analysis. What does our motion look like when we graph it? So let's start with an example. An arrow is launched vertically upward. It moves straight up to a maximum height, and then it falls to the ground. The trajectory of our arrow we've got noted here. Which graph best represents the vertical velocity of the arrow as a function of time? We're going to forget about air resistance. The only force we have is gravity. Okay, so remember, we've gone through a couple of examples of this. Our arrow has a non-zero positive velocity when it's launched. It moves upward, its velocity is decelerating, its velocity is decreasing, okay? And then it reaches this point here just as it turns around. And when it reaches this point, its velocity becomes zero. So its velocity decreases from here to here. It was positive, decreasing to zero. And then it's going to fall back down towards the ground, okay? And so its velocity was zero here, and then as it's falling towards the ground, it's going to increase, the magnitude will increase, but it's going to be a negative velocity because it's in the negative y direction, okay? So which of these graphs best represents that motion? Well, we start from positive, we go to zero, and then we end up negative. So we can't use A here because it starts at positive, goes to zero, and becomes positive again. We don't want that, okay? Here, we're positive, and then for some reason we are zero velocity for some period of time, and then we go to a negative velocity, almost but not quite. This change in velocity from positive to negative moving through zero is instantaneous, so we're not going to be hovering at that spot here, okay? And we're certainly not going to be E here where we are positive velocity and then increasing to a maximum velocity up here and then decreasing as we fall, because we know that our velocity at the apex here has to be zero. So then we're left with either C or D. So C, we see here that the velocity, it looks like it's not decreasing at a constant rate as we get towards zero, okay? It's increasing pretty fast here, and then that increase seems to slow down as we get through zero. And then it's saying that that velocity is again sort of slow, and then it gets faster as it falls back toward the ground, okay? So this would indicate that the velocity, the rate of change of velocity is not constant. If the acceleration is constant, that means that the rate of change of velocity is the same, okay? The rate of change of velocity is the same. That means that our velocity graph has to be essentially, have a slope that is a constant slope, okay? And so we know then that D must be the answer here, because our velocity is impacted by the acceleration. If the acceleration is constant, that means that our rate of change of velocity is also constant, okay? So then we have this graph to represent the motion of our arrow as we launch it upward, it reaches zero velocity, and then it comes back downward again. So I was just talking about the slope of our velocity versus time graph and how an acceleration is a rate of change of velocity. So slopes show rates of change. Slopes of a line show rates of change. Here we have our x and y axis, and we have a line. And if you remember the equation of a line, the equation for a line is y is equal to mx plus b. Y is our y position on the graph, x is our x position on the graph, m is the slope of the line, and then b is the y-intercept, where we cross the y-axis here, okay? So the slope, you might remember, is the rise over the run. It's your change in y-axis over the change along your x-axis. That gives you the slope. So the slope of a graph of velocity versus time, which is what we were just looking at, is the acceleration. And so we had, instead of y on this axis, we had v in our previous example. and this was t. So we could use our equation y is equal to mx plus b, and where we see y, we can swap that out for v final. And then our b, our y-intercept, would be our initial velocity, okay, if this was our v-axis. And then our coordinate along the horizontal axis would be our time, okay? And then our slope would be represented by our acceleration. Well, this is our equation. V final is equal to V initial plus acceleration times time. And we can always rearrange that to show that acceleration is equal to the change in velocity over the change in time. So the slope of a velocity versus time graph, like what we just looked at, would give us our acceleration. Similarly, the slope of a graph of position versus time is velocity. So if we swapped out for the horizontal axis, we instead here said this was time. If we swapped out the vertical axis and said that was x, then we would find that our velocity is equal to our rate and change of position, our x position, over the change in time. That would be the slope of a line if we plotted position on this axis and time on this axis, okay? So remember, slope of a graph of position versus time is velocity. Slope of a graph of velocity versus time is acceleration, okay? So here I have a couple examples. Here we have the position of a car versus time, okay? And we have the plot here shown of the position over time. And then at any place along here, between any 2 points, we can calculate the slope, the rise over the run. That slope would give us the velocity between those points, okay? Then we take that velocity, which was the slope of this line, and then we can plot it down here. We see that that velocity is not constant, which means that the slopes of these lines were not constant. Over time, the slopes of this line increased, which means that the velocity must also be increasing. Now we can take the slope of our velocity versus time graph to give us the acceleration. So between any points here, if I take the rise over the run, I see that the rise over the run is going to be constant. It's going to be the same. So that means that our acceleration is constant. So then if I plot the acceleration here, it's just going to be a horizontal line because our slope of the velocity versus time graph was constant, okay? So that is an example of how you can show rates of change and how you can plot position, velocity, acceleration versus time, and how you can use those graphs to help you interpret velocities and accelerations. So now we're going to work through an example, okay? I'm going to give you a graph of velocity versus time of a ship coming into harbor. So let's describe the motion of the ship in words based on this graph. So remember, this is velocity over time, okay? And so what we see here at time t is equal to 0, the ship is moving at a constant velocity here of 5 meters per second from 0 to 3 seconds. Then it begins to decelerate at a constant rate. That's a straight line here. It's decelerating where its velocity is decreasing. And the slope of this line is negative, which means that our acceleration is negative. We're decelerating. And then as we go from 5 to 10 seconds, we are still decelerating. The slope of our line is negative. We're slowing down, okay? But the rate of deceleration decreases. So our acceleration is not constant between times 3 to 5 seconds and times 5 to 10 seconds. Our acceleration is changing. So at some point here, 5 seconds, the deceleration rate decreases. And it maintains this lower deceleration until we stop, come to a stop at 10 seconds right here as we rest in harbor. So your question is, what would a graph of the ship's acceleration look like? Remember that acceleration is the slope of the velocity graph because acceleration is the rate of change of velocity. So we already have our velocity versus time graph here. And so what you're going to do is calculate the slope then between time 0 and 3 seconds, between 3 seconds and 5 seconds, and then between 5 seconds and 10 seconds. So the slope of that velocity versus time graph will give you the acceleration. And so you're going to find the acceleration between those 3 time intervals, and then you could also think about plotting it too. But remember that the slope of the velocity versus time graph gives you the acceleration.